Here we are going to learn about latches, flip-flops, memory and state machines, and how they can be applied in digital circuits. First, let's talk about memory elements. Memory elements are elements that store memory or state information. And also, the output of an element depends not only on the current input. So, let's put this in the context of traditional combinational logic. Say we have a digital logic circuit shown as a black box that has some number of inputs and one or more outputs. If an input variable changes here from 0 to 1 or 1 to 0, we will see a change out here in this output vector immediately. There's a problem though in that if there's any change at the input, we see an instantaneous change at the output. Sometimes we might want to change the input here and have no change at the output instead. In this case, we want to use an element that does not depend only on the current input. The output of memory elements depend not only on the current input, but on previous inputs. Some examples of these are registers, RAM, or random access memory, and the cache, the memory cache. If we look at a MIPS architecture, for example, a CPU architecture here, we can see it's composed of traditional combinational logic circuits and also circuit elements that store memory or state. So some examples of components that store state would be this program counter here. Another would be the instruction cache, which stores a list of instructions in memory. Main memory, which is accessed by the instruction cache or the data cache. Also, the data cache would store information that does not change with time. The instruction register would store the current instruction to execute, and also the register file here. Depending on the implementation of the CPU, the control unit may or may not have memory elements, and the ALU and these multiplexers, these hardware if-else statements, if you will, are often only combinational logic. So what is a register? It's very similar to memory. A CPU, let's think about it. A CPU has components that store sets of bits, i.e. ones and zeros. It is often used for storage of variables in computer programs. So if you were to implement a for loop, for I equals 0, I is less than 10, I plus plus, for example, and then you would continue your code like so. This variable here is an integer that is 32-bit in our supposed CPU architecture for MIPS, and it can be stored in a register. Storage of information, and it is synchronized to a CPU clock. And the information is often stored at the positive edge of a clock signal, though sometimes it is stored at the negative edge. What would be the inputs of a register? Well, we have some D inputs, and then we have our output, which outputs the current value of the register. These values can change, and these values will not change. The only time these outputs here change is when some event happens at the clock. Only when clock changes 0 to 1, also called the rising edge, does Q0 to Q7 change. So combinational versus sequential circuits. If we had a sample digital logic circuit here that's combinational, we could say we have an XOR circuit here and an XOR circuit here. Let's say this is for the calculation of S in an adder. Notice that if either A or B or C in change, then we see an immediate output here on S. S will immediately change. However, when we have a sequential circuit, if we have a input here and a clock input here, let's say we have an A and we have a B here. This is input B. And input C in. And we connect all of these to clock. Then we would have these going to our combinational logic here. Notice that our output S would not necessarily change immediately until we saw a change on the clock. Remember that our memory elements will not change the output here until, or the outputs of these memory elements will not change until the clock is activated. How do we create memory elements? Well, let's look at latches. The RS latch, also called an SR latch, is created by connecting two inverters in a feedback stage. Now why, or two NAND gates or two NOR gates in a feedback topology like so. We can simplify this further if we think of two inverters feeding back on each other. Let's just do this. Two inverters. If we have a 1 here, then we're going to have an output of a 0, but the 0 input here comes as a 1 output here. 0, 1, 0, 1, 0 to 1 to 0 to 1 to 0 ad infinitum. So this feedback circuit holds a 1 or 0 value. It's possible to, instead of having a 1 here and a 0 here, we could have a 0 at this end and a 1 at this end instead. 0 becomes 1, becomes 0, becomes 1 again, becomes 0, becomes 1 again, and we have a infinite feedback loop. Two inverters feeding back on each other is not necessarily practical, however. We need some way to control it. The way we control it is to use a second input, and we can use the NAND gate or the NOR gate as control inputs for our latch. So in our SR latch, we can see what happens when we have an input of 0 here and an input of 0 here. 0 ANDed with anything is 0, but inverted, here we're going to get a 1. 0 ANDed with anything is 0, but inverted, we get a 1 again. So this is what we're going to call the weird state. We are actually not going to use this in practice. Instead, we need to use these other three cases here. The set state, the reset state, and the hold state. Let's look at an interesting case here when we do a feedback path like so, and we set this input as 1 and this output as 1. Notice that 1 ANDed with anything, say this is Q and this is Q prime. 1 ANDed with Q is going to give us Q, but inverted gives us Q prime instead. 1 ANDed with Q prime gives us Q prime, and then we invert Q prime and we get Q. And so we can go back and forth between Q and Q prime, and we hold the value. But now, how do we set the value? Let's try setting this input to 0 and leaving this input at 1. Zero ANDed with anything is 0. Inverted gives us 1. 1 and 1 equals 1, but then we invert on the NAND gate, so we get 0. And then we AND 0 with 0, and then we get 0, we invert again, we get 1. So 1 and 0, we go in our feedback path. Notice this is very similar to our feedback with the inverters. Let's draw this differently so the feedback is easier to see. So all I did in this drawing is I twisted this bottom inverter, and now we have the crossing wires. This is the set condition. What about if we wish to set Q equal to 0? We can draw this here. 2 NAND gates. Let's draw our feedback paths. 1, because we don't wish to set, but we wish to reset, so we place a 0 here. 0 ANDed with anything is 0, but when we invert it, we are going to get 1. 1, this 1 ANDed with 1 is 1, and if we invert, we get 0. Notice that the feedback gives us 1 again, then 0 again. So we have this we shall call the Q variable. We'll say that Q is equal to 1 here, Q is equal to 0 here in the reset condition. And here at the top, Q holds its value regardless of anything else happening in the combinational circuit. Q is not going to change until the S variable input or the R variable input are appropriately set. Now this is very useful for setting and resetting, but this is an asynchronous latch. That means there's no synchronization to a clock signal. The D latch is an augmented version of the SR latch. Notice that the SR latch, we have two input NANDs, and that it's included in the D latch here. But there's some extra circuitry here. We have some NAND gates, and we have an inverter. Well, first of all, why do we want to have a D? Well, notice that if we wish to set or reset the state, S and R need to be inversions of each other. The D basically develops our S signal and our R signal. First of all. Now the S or R signal, when we develop these, must be equal to 0 and 1 or 1 and 0 when we wish to set the state of our latch. If we wish to not set the value and have it hold its state, they must both be 1. Okay? Let's come to the hold state in just a moment, but if we wish to set or reset, we could say this is 0 and this is 1, or this is 1 and this is 0, and it will set or reset the latch very quickly. However, if D changes, then the latch is going to change immediately. So to fix that, what we're going to do is add another set of AND gates here. We'll call this an enable signal. Now if we have two AND gates here, En equals 0. Let's change our names from S to S1 and R to R1 here. Then we get S and SR here, S and R here. Notice that if En is equal to 0, this will imply that S equals 0 and also that R equals 0. If we wish to change it so we get S equal to 1 and R equal to 1 instead, we can first invert these AND gates so we get NAND gates instead. So En equal to 0 is going to imply that S equals 1 and R is equal to 1. So this would be the hold condition. En equal to 1 implies S equals d prime r equals d here, and q is then set equal to the value of d. And the truth table for this D-latch circuit is given here. Problem with the D-latch, unfortunately, is that if you have two D-latches connected to each other, so this is latch 1 and latch 2. Notice that if you just connect them together directly and then connect the two enables together, it becomes transparent. This D value, when this changes, will cause this Q value to change immediately. And we don't like that. So notice that the D latch contains 5 gates here, and the D latch contains 5 gates here. Let's say instead we wish to make the latches make a logic element that is non-transparent and doesn't just have the latches trip like dominoes. We can put two latches together and add a little extra logic. Notice here we have latch 1 and here we have latch 2. The enable signals on both of them are inverted. This inversion, we have En prime and we have En here. Not En, not prime. So En prime and En. So when this latch is transparent, this one blocks. When this one blocks, this one is transparent. Hence the term flip-flop. It flips from here to here. Back to here again, back to here again. It flip-flops between which latch is active. Only one D latch is active at any given time. Now notice, as a shortcut, this circuit is slightly optimized because this inverter is not here. The value, or the inverted value, comes from this NAND gate instead of from an extra inverter. Latches and flip-flops, generally speaking, hold both Q and Q prime. So if you have a variable and you need its inversion, you don't need an extra inverter in most cases. If we wish to consider a flip-flop that we can asynchronously set to 0 or 1, we can augment it even further. Notice that here we have a set signal and a reset signal. The SR latches here and here now and here now use 3 input NANDs instead. Let's think about a large-scale digital circuit, maybe a CPU. If we wish to reset the system, we need to set it to a known state. Setting it to a known state can be incredibly difficult without planning ahead in the synchronous digital circuitry. However, if we use the set and reset signals, it's possible to flip a single switch and set each digital value or each register value to a known state. Maybe in your programming classes you have heard that you must always initialize your variables. Rule: always init variables in software. The reason is that this D flip-flop can come on in a random state. Because it can be turned on in a random state or be set arbitrarily in your program, sometimes it's necessary to return it to a known state. Use set, also called preset, and reset, also called clear, to return system to a known state. So in the previous example, we had a 46 transistor D flip-flop. A different implementation, instead of using 2-input NANDs, 3-input NANDs, and multiple inverters, it's possible to use a set of 6 3-input NANDs instead. This is a more efficient version of the D flip-flop and uses a total of only 36 transistors. Our device symbol for our D flip-flop, look closely. We have our inputs D, our clock input here, our output Q, our output Q prime, which is always the inverse of Q, or should be. We have an asynchronous set, which is not timed to the clock, and an asynchronous reset, that is not timed to the clock. So set prime, notice that, and reset prime, notice that these are inverted, so these are called active low. Set value of flip-flop when input is 0. So Q will become 1 when set prime is 1, or set prime is 0. Set prime equals 0 implies Q equals 1. Reset prime equals 0 implies Q equals 0. So the D flip-flop characteristic table is simply defined here. The D flip-flop characteristic table is defined here. Q relates to D at the rising clock edge. If D is equal to 0 at the rising clock edge, Q will equal to 0. If D is equal to 1 at the rising clock edge, Q is equal to 1. The characteristic equation of the D flip-flop is Q equals D. And a standard implementation is shown here in 7400 logic. But how do we think about registers? How would we construct a register? Well, let's say we wanted an 8-bit register. A flip-flop stores only 1 bit. If we wanted to store 8 bits, we could use 8 flip-flops. Like here, 8 flip-flops. Combine those together somehow and we get an 8-bit register. How would we do it? What we could do is line them up. 1, 2, 3, 4, 5, 6, 7, 8. We have a D value for each of these. Then we have a clock value represented by C. The clock is connected all to the same wire, all to the same clock input, all to all the clock inputs of the D flip-flops. So let's connect our clock. Our D inputs are brought out as inputs to our higher level circuit. D7, D6, 5, D4, D3, 2, and so on. We have our Q outputs. And these would connect to Q7, Q6, Q5, Q4, etc. And then we would need our clear or reset. We'll call this R. R. This is at the bottom. And our reset signal, reset signals on all our flip-flops all connect to the same reset signal at the higher level. So clock, reset, prime, set prime, is not used here on the register. So set prime on each flip-flop should be equal to 1. Digital logic 1. This constant will ensure that the flip-flops are never set equal to 1. So let's talk about sequential circuits. They are circuits that contain memory information and update through time. They consist of combinational elements and sequential elements. Combinational elements are memoryless components that can change immediately as soon as that change their outputs immediately as soon as an input change. Sequential elements are components that have memory included. The memory does not change, the memory components do not change their outputs until a clock signal is received. Sequential circuits follow a general structure. They have a combinational component here, and then they have a register with some number of bits. This register with some number of bits was developed in this presentation earlier. It is merely an array of memory elements or an array of registers. We can call it an array of flip-flops. What about the combinational elements? Well, the combinational element standardized ways or methods are already available for combinational circuits. What kinds of methods are available? Well, let's name some. Truth tables, Boolean expressions, and K-maps. One that we haven't talked about yet are state diagrams. These are specific to state machines and show how the system evolves with time. This will be covered in this video very briefly. But we already have the tools for managing combinational elements with truth tables, Boolean expressions, and K-maps. So let's take a look. Let's say we wanted to create a circuit that counted from 0 to 7 and then wrapped around to 0 again. Let's draw it as a state diagram. 0, 0, 0 for the first state, 0, 0, 1 for the next state, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 5, 1, 1, 0, 6, 1, 1, 1 for 7. We start in state 0. Then we cycle from 0 to 1, 1 to 2, 2 to 3, 3 to 4, 4 to 5, 5 to 6, 6 to 7, and 7 back to 0. We can translate this to a truth table by saying we have 3 input variables to our Boolean logic. Well, let's look here. You have, for any number from 0 to 7, you have 3 bits, B2, B1, B0, right? If we use flip-flop variables, we can call these Q2, Q1, and Q0 instead. So let's stick with the Q2, Q1, Q0 names instead. The next state transition, so this is our transition. Our input is 0, 0, 0. Our next state is 0, 0, 1. So these would be our inputs. Our next state variables, D2, D1, D0, would be for the next state. So current state, next state. And we could say the output is the same as the current state and simplify our lives. What does this imply? This implies that O2 equals Q2, O1 equals Q1, O0 equals Q0. And what we have is a truth table. We have 3 input variables and 6 output variables for our Boolean logic. 3 input variables and 6 output variables. So because O2, O1, and O0 are already taken care of, we only need to optimize D2, D1, and D0. Let's take a look at D2. D2, we have Q2, Q1, Q0. Let's create our K-map. So we have 0, 0, 0, 1, 1, 1, 1, 0 for D2. For D1, we have Q2 as input, Q1, Q0. Zero, 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 1, 1, 1, 1, 0, 1. So I'm just going to copy, before I just copied this column, now I'm going to copy this column. 0, 1, 1, 0, 0, 1, 1, 0. Okay, and then D0. 2, Q1, Q0. Zero, 1, so 0, 0, 0, 1, 1, 1, 1, 0. 0, 1. Let's look here. Should be copying this column. So I'm copying this column here from the top. It is 1, 0, 1, 0. And 1, 0, 1, 0. Let's box this here. We see that D0 equals Q0 prime. Next we can look at D1. We'll grab these two. D1 equals Q1 Q0 prime, or Q1 prime Q0. This is the same as Q1 XOR Q0 for D1. Finally, we have one group, two groups, and three groups. D2 equals Q2 prime Q1 Q0, or Q2 Q1 prime, or Q2 Q0 prime. And we have our Boolean algebra equations. So let's see if we can draw the circuit. We have D2, D1, and D0. How many flip-flops do we need? We need 3. Let's draw 3 flip-flops. One, 2, 3. We have D, clock. You can draw this with a triangle here. Q, Q prime, Q, Q prime, D, clock, Q, and Q prime. Now what we can do is bring these variables back. And they become inputs. We can bring these variables back and they become inputs to our circuit. Now we have all of our variables and their inverses. This is Q2, Q2 prime, Q1, Q1 prime, Q0, Q0 prime. These are our input variables, and we have our, or these are our output variables, and we have our input variables. So D, let's say D2. This is a little bit complicated. We have 3 AND gates, so 1, 2, and 3. We need Q2 prime, Q1, and Q0. Now we have Q2 with Q1 prime and Q2 ANDed with Q0 prime. We just copied this equation. OR these together, and we have the value for D2. This is our output. O2 here. Next we have D1. It is simply an XOR gate Q1 XOR Q0. And then we have D0, which is equal to Q0 prime. The clock signal is shared by all 3 flip-flops. O1 is equal to Q1. O0 is equal to Q0. Don't forget the clear signal here. Call that R for reset, reset, and reset. And the set signal is left off. So R and clock. And we have now a counter circuit that counts from 0 a counter circuit that counts from 0 to 7 and wraps around. Every time clock goes from 0 to 1, the counter increments. Here completes our introduction to flip-flops, memory, and latches. As a little addendum, let's try simulating the circuit that we just developed now. So first of all, we're going to start in state 0, 0, 0, which is our initial state. Notice that we have a reset signal, which is connected to 1, 2, 3 flip-flops here. And if we set this to 0, it should set these output bits to 0 here. We have output 2, output 1, and output 0, O2, O1, and O0. Notice that all our input variables to the combinational logic are brought over here from the flip-flops. They've been wrapped around. So we are ready to try simulating. We've got all our combinational circuits implemented here as well. Let's pull out of the reset state. So because it's active low, we need to set the reset signal to 1, and now we can try clocking. So this is our clock signal. When it transitions 0 to 1, 0 to 1, 0 to 1, we should see these three values change. So 0, 0, 0 should go to 0, 0, 1. Let's try it now. Let's click on the clock. 0, 0, 1. When we go 1 to 0, nothing should change. And we see it stays at 1. When we click again, it should go to the state 2. We go from 0, 0, 1 to 0, 1, 0. And we can go to state 0, 1, 1, 0, or 1, 0, 0 next. 1, 0, 1, 1, 1, 0, and then 1, 1, 1. Our final state, our final transition is 1, 1, 1 to 0, 0, 0, and we've wrapped around again. So we can click this binary switch and clock the system as many times as we like, and this state machine will keep counting from 0 to 7 and wrapping around again till the end of time, or we decide we're tired. What if we wish to reset the system though? Say we're in state 0, 1, 0. I want to go to a known state. We can use the reset signal. We can go from 1 to 0. And look, we have 0, 0, 0. Set it to 1 again, and now we can clock the system again, starting from 0, 0, 0 to 0, 0, 1, 0, 1, 0 to 0, 1, 1, and so on. What happens if we leave it in reset? We are in state 0, 0, 0, and no matter how the clock changes, notice that our output signals do not change because the reset signal is engaged. And so we see that the sequential circuit, the sequential counter that we developed, in fact works.